In the lecture so far, we had taken a look at the basics of group theory, the definition of a group, some of its basic properties, and in particular, in the last lecture, we had taken a look at the most important substructure which a group has, that is the notion of a subgroup. A subgroup, of course, is a subset which is also a group in its own right. Now, intimately connected with the notion of a subgroup is a notion of congruency modulo a subgroup, which leads naturally to some other sets which reveal the structure of a group very nicely. These sets are called cosets. Now, this congruency modulo a subgroup is an equivalence relation. In the next half of this lecture, we are going to take a look at another equivalence relation, that of conjugacy. Both of these kinds of equivalence relations will break the group up into partitions. The first kind of partition is our next topic, that is the coset. So what exactly is a coset? For a subgroup capital H of a group capital G and any small g which is an element of capital G, the left coset small g h is defined to be the set which is given by this. Small gh, set of all the elements small g times h, where h belongs to capital H. What this means is you take every one of the elements of the subgroup capital H in turn and multiply them on the left by small g, and this collection of elements that you get is the left coset corresponding to the element small g. Of course, there is nothing special about left cosets. We can also similarly define right cosets. Right coset is denoted by capital H followed by small g and is defined to be the set of all elements small hg, where small h runs over the entire subgroup capital H. Now, in general, for a given element small g of capital G, h small g, the right coset with respect of small g is different from small gh, which is the left coset of small g with respect to the subgroup capital H. Now, just to illustrate this, let us take a look at the example of the symmetry group of an equilateral triangle that we have talked about. Of course, we need to pick a specific subgroup for this, and let's start with the subgroup small e and a. So these are the two elements in your subgroup, small e and the reflection a. Here you can see the multiplication table, and let's try to work out the left cosets and the right cosets one after the other. So what is the left coset corresponding to small e? Remember, that means you are going to take small e and multiply the elements of capital H, which are small e and small a, one after the other by small e on the left. So basically you want elements like EE and EA. So you're going to look at the elements EA, and you're going to look at what happens when you multiply them from the left by E. So basically this is what forms your subgroup, and to get the coset you're going to multiply each one of these elements on the left by small e, and you get small e and a. That's sort of obvious. What about the corresponding right coset? For the right coset, you will take the subgroup element first, so small e and a from here, and multiply them on the right by small e. So capital H E is again obviously EA from this picture. Not really very interesting. It's obvious that if you multiply elements of a subgroup either on the left or on the right by the identity, you're going to get the subgroup back. A bit non-trivial is the fact that if you were to multiply the subgroup capital H by A on the left or A on the right, you will again get the subgroup back. It's slightly more non-trivial than multiplying by identity, but it should be obvious. This basically follows from the fact that we are talking of a subgroup after all. So, if you multiply by A on the left, the subgroup EA, I'm going to get AE, but remember this is a set, so the order doesn't matter. You get the same left coset as you had with the identity. What about HA? Again, exactly the same, back again. By the way, if this had been a subgroup with more than two elements, and you had picked any one of the elements to form the left coset or the right coset, you would get the subgroup back. That's just closure of the subgroup under multiplication. Well, things get a bit less trivial if you look at cosets of elements other than those which already belong to the subgroup. So, for example, if you take the element small b, the left coset here is simply bf. The right coset is bd. Notice that here the left and right cosets are different. Well, ch will give you cd, hc will give you cf. By the way, one thing you should have noticed by now, that the element for which we are taking the coset is always in the coset, and that's again obvious because the identity is always in the subgroup. So ch has c in it, so does hc. Well, dh is cd, again dh has d in it, hd is bd, fh, bf, and hf, cf. And so now notice that the cosets are repeating, right? EH and AH have the same left coset, BH and FH have the same left coset, CH and DH have the same left coset. Right cosets do not match the left cosets, but the same feature is there again. EA is the right coset for both E and A, that's sort of obvious. BD is the right coset for both B and D. CF is the right coset for both C and F. And if you take all of them together, you notice that every one of the elements of the group are covered. So the union of all the left cosets on the one hand and all the right cosets on the other hand is the entire group itself. These are of course special cases of a general result, and we are going to see why soon. You can of course find out cosets for the other subgroups like EB and EC. They will of course be different from these cosets, but the idea is very, very similar. And in all these cases, you will find the same features that we talked about right now. Let me just finish this example with a 3-element subgroup, or cosets for a 3-element subgroup, namely ED and F. So what are the left cosets? Well, for EH, you get EDF, right coset, EDF again. No surprises there. AH actually has ABC, HA has ABC back again. So here in this case, the left and right cosets match. In fact, if you went along and found BH, you will again get ABC. HB is again ABC. By the way, the fact that AH and BH, the two left cosets here, are the same is not a surprise. Instead of A, you are using B here, but B is already a member of this coset, and you are going to get the same coset back. The reason we are going to should be sort of obvious, but we are going to formalize this soon. CH is again ABC, HC is again ABC. DH, HD, FH and HF are EDF. Once again, notice that the cosets are completely disjoint or identical. These three are identical, these three are identical. They're completely disjoint from each other, and their union is the entire set. And in this case, there is no distinction between left and right cosets. Now, the common features that we see for both sets of cosets for the two subgroups that we have examined, namely that the cosets partition the group, that's of course not an accident. There is something deeper at work here. Let me just explain to you what partition means. A set is said to be partitioned if it is broken up into subsets which are mutually disjoint and whose union gives you the entire set. In the two examples that we have seen so far, cosets of the subgroup EA and cosets of the subgroup EDF, the common feature was the cosets were mutually disjoint or identical, and if you took the union, you would end up with the set underlying the group in both cases. Now, of course, this is not an accident. And the deeper thing that is at work here, as in the case of all partitions of sets, is that there is an equivalence relation underlying this whole thing. The particular equivalence relation that we have in this case is called congruency modulo a subgroup. So we start with the general statement that if G is a group and H is a subgroup, this notation that we have here, H less than G, is actually a notation which is often used by many authors to signify that H is a subgroup of G. By the way, this does not imply proper subgroup or a subgroup which is somehow smaller than G. It also includes G itself. So H is a subgroup of G. That's what the less than sign here implies. Now, given this scenario, two elements small a and small b of G, of the group G, are said to be congruent to each other modulo the subgroup H if the following holds. If A times B inverse is an element of capital H, then A is said to be congruent to B modulo H, and this here is the notation for that. Of course, this means that there is an element small h in capital H such that A is given by small h times B, and this is going to be very important in order to connect this with cosets. Now, what we need to show first is that this relation that we have defined, this relation between two elements of a group, congruency modulo H, is an equivalence relation. Just to remind you, an equivalence relation is a kind of glorified or generalized equality. A relation is said to be an equivalence relation if it satisfies three conditions: reflexivity, symmetry, and transitivity. Let us check each one of them in turn. Reflexivity. Okay, is this relation reflexive? That of course means that every element of the group is related to itself. Is that true? Well, if you take any element small g of capital G, then GG inverse is identity, and the identity of course has to belong to the subgroup capital H. So, every element is related to itself. This relation is reflexive. What about symmetry? This relation is symmetric if A is related to B implies B is related to A. But if G1 is related to G2, so G1 G2 inverse belongs to H, then G2 G1 inverse, which is nothing but the inverse of G1 G2 inverse, has to belong to H. So finally, transitivity. Is this relationship transitive? That is, if G1 is related to G2 and G2 is related to G3, is G1 related to G3? Of course, G1 is related to G2 via this congruency modulo H relation, means G1 G2 inverse belongs to H. G2 is related to G3 means G2 G3 inverse belongs to H. But what about G1 G3 inverse? Well, G1 G3 inverse, as you can easily see, is simply nothing but the product of these two operations, G1 G2 inverse and G2 G3 inverse, and of course that belongs to H. Simply because capital H is a subgroup, so product of two elements in capital H must belong to capital H. So this is an equivalence relation. Now, for any equivalence relation on a set S, now we are moving away from group theory, or moving back really to elementary mathematics, elementary set theory. If you have an equivalence relation on a set S, this gives rise to the concept of an equivalence class, class A, for any element A of S. So what is this equivalence class? This equivalence class is just the collection of all the elements of S which are related to A by this equivalence relation. Now, equivalence classes have very important features. They provide a partition on the set S. That is, they break up the set S into mutually disjoint pieces. First, the important thing is every element belongs to an equivalence class. If nothing else, it belongs to its own equivalence class, right? Because every equivalence relation is reflexive. So A must be related to A So the equivalence class of A must contain, if nothing else, at least the element A. And this of course means that if you take the union of all the equivalence classes, you must get the entire set back, because every set is somewhere or the other in this collection. Now the other important result is equivalence classes are either disjoint or identical. In order to show that, let us just assume that you have two equivalence classes, that of A and that of B, and these two equivalence classes are not disjoint, which means the intersection is not empty. So if it is not empty, then of course there will be an element, let's call it C, in that intersection. This of course means that C is actually in the equivalence class of A and also in the equivalence class of B. Since C is in the equivalence class of A, it's equivalent to A under this relation. It's also equivalent to B under this relation. But using the fact that equivalence relations are symmetric and transitive, this immediately tells you that A has to be equivalent to B, which means A and B must belong to the same equivalence class in this case. So the equivalence classes of A and B, if they are not disjoint, must be identical. So here we see that equivalence classes naturally provide a breakup of the set into disjoint pieces, such that when you put them together, you get the entire set back, which of course is what a partition really is. So as I said, the reason why we are looking at equivalence relations all over again now is that cosets essentially arise as equivalence classes for a particular relation, and no point for guessing which one is conjugacy modulo the subgroup H. If for a group capital G and a subset H of G, which is also a subgroup, A and B are congruent modulo H, that means AB inverse belongs to H, but that also means A belongs to the right coset HB. And a very little thought will show you that the right cosets are equivalence classes for the equivalence relation of congruency modulo H. Now I have stated this for right cosets. It should be very easy for you to figure out what the equivalence relation is for which the left cosets are equivalence classes. But for the time being, let's stick to this one. Right cosets are equivalence classes. That means they partition the group, or to be more precise, the set underlying the group. Now all this is valid for both finite groups and infinite groups. But let me now focus on finite groups in particular. Now if the group G is finite, then the subgroup H of course has to be finite. And now all right cosets HG of a subgroup H will end up having exactly the same number of elements as capital H. Now why is that the case? Well, you start with a finite number of elements in capital H, let's say H1, H2 up to H, say K, and you multiply each one of them from the right by G to get the elements of the right coset capital HG. So H1G, H2G, etc., HKG. Nominally this looks like exactly K elements, the same number of elements as in H itself. However, we have to figure out whether there are any repeats in this or not. Remember that groups allow cancellation. What that means is if any two of these elements, say HIG and HJG, were equal, then you could cancel out the G by hitting with G inverse on the right, and you would end up getting HI equals AJ. This means that there can be no repeats. Hence, all the K elements in the coset that you get, H1G, H2G up to HKG, are all distinct elements. So hence, the number of elements in the coset is exactly the same as the number of elements in the original subgroup capital H. So what do you have now? The entire group capital G has been broken up into right cosets, each of which have exactly the same number of elements as capital H, and the union gives you the group capital G back. So we end up with this result that the order of a subgroup must divide the order of the group. This result goes by the name of Lagrange's theorem and happens to be a very, very important result in abstract group theory. It's not really so important for us for physical applications. However, we are going to illustrate its power by establishing one very important result. But before I do that, let me warn you that the converse of this theorem is not true. Just because the order of a group is composite does not mean that there is a subgroup corresponding to every number which divides that order. Now the important result that I was alluding to, this result, stated simply, is that every group of prime order is abelian. Now how do you prove this? Well, you start with a group of order P where P is a prime and pick an element small g of P which is not the identity. Remember, prime numbers are all bigger than 1, which means that there is an element which is other than the identity in my group. And this element will of course have an order, let's call that order small r. And this small r of course cannot be 1 simply because the only element which has order 1 is the identity itself. So now what we can do is we can construct the cyclic subgroup corresponding to this generated small g, that is the set small g, g square, g cube up to g to the r, which as we know forms a subgroup under the same multiplication rule as in capital G. However, according to Lagrange's theorem, the small r must divide P, right? Because small r is the order of this cyclic subgroup and P is the order of the whole group. Now, since P is a prime number, the only number other than 1 which divides it is P itself. So, R must be equal to P. What that means is that capital H must be exactly the same set as capital G itself. So, H and G must be the same group. So, the cyclic subgroup generated by any one of its non-identity elements for this group G must be the same as the group G itself. So, group G is cyclic and hence it must be abelian. Proof complete. As we have seen, the notion of congruency modulo a subgroup is an equivalent relation, and as a result you end up with some partitions of the group. These partitions of course are the cosets that we have been talking about so far. Now there is another very, very important equivalence relation that you can define on a group, and this is what is called conjugacy, and this also provides the group with another partition, and the partitions here are called conjugacy classes. Conjugacy classes happen to be very, very important, especially in the theory of representations of groups, which is going to form a major part of our course, because ultimately a major part of the application of group theory to physics is via group representation theory. First, the notion of conjugacy. The element G2 is said to be conjugate to an element G1. Of course, both of these are elements of a group capital G. If there exists in the group capital G some element small g, such that G2 is given by G, G1, G inverse. So this particular operation is called conjugacy via the element small g, or is also called more formally an inner automorphism corresponding to the element small g. Now the nomenclature inner automorphism of course presupposes that we have discussed the notion of automorphism first. Since we have not come to that as yet, we are just going to take that as a name. So we will stick for the time being to conjugacy mediated by the element small g. Basically G2 and G1 are conjugate to each other if there is an element small g in the group which mediates this conjugation. That is, if you left multiply G1 by G and right multiplied by G inverse, you end up with G2. Now this particular relation between elements happens to be an equivalence relation as well. How do we know that? Well, you can easily check that it follows all the basic properties of an equivalence relation. That is, you need to check that is reflexive, it is symmetric, and it is transitive. To prove that this relationship is reflexive, you have to find one element in the group capital G such that any element G1 is related to itself. Now that's very easy. All you have to do is use the element E, which belongs to every group capital G. So G1 is of course E G1 E inverse, which means G1 is conjugate to G1. Hence, reflexivity is satisfied. What about symmetry? If G2 is G G1 G inverse, it's very easy to see that G1 is G inverse G2 G. But since G on the right here is actually the inverse of G inverse, this really is of the form G1 is G inverse G2 G inverse inverse, which means that in this case is G inverse which mediates the conjugation. Since every element of the group has an inverse, this symmetry of the conjugacy relation works nicely. It's very easy to check along similar lines that the relation is also transitive. So because you have reflexivity, symmetry and transitivity, this relationship, of course, is an equivalence relation. Now that we have seen that if conjugate 2 is an equivalence relation, it naturally follows that there will be equivalence classes corresponding to it. The equivalence classes corresponding to this particular relation are called conjugacy classes. And as we will see later, they will play a very important role in the theory of group representations, which is our real reason for being highly interested in them. For the time being, let us just take a look at the formal definition of a conjugacy class of an element small g. We write that as for all equivalence classes with a square bracket around small g. So square bracket around small g denotes the equivalence class of the element small g of a group. And that is of course all the elements g prime of the group such that there exists some g bar in capital G which actually makes G prime conjugate to G, or which mediates the conjugation between G prime and G. So if we can find such a G bar, then G prime belongs to the same conjugacy class as G. Now, it's very obvious that the identity element always has to be in a class by its own, because no matter what G you pick from your group capital G, small g times E times small g inverse, the element conjugate to E will always be E itself. So in every group, the identity element always sits in a singleton set as its own conjugacy class. Well, on the other hand, the other extreme is when we talk about abelian groups. In an abelian group, every element is in its own conjugacy class. Hence, every class in the abelian group has only one element. And that's also very easy to see. Whenever you try to conjugate an element of an abelian group by taking G bar, G bar inverse, the G bar and G are going to commute. And so the G bar is going to sit right next to G bar inverse and cancel it, giving you back G. Now, just to get some feeling about what conjugacy classes are all about, let us now take a look at conjugacy classes for our familiar group, the group with which we started discussing groups in the first place. The set of symmetry elements or symmetry operations on an equilateral triangle. Let me just quickly remind you that this group had 6 elements, 3 reflections A, B and C, and 3 rotations, E doing nothing, D 120 degrees, F 240 degrees. And we had actually built up a complete multiplication table for this in a previous lecture. Now, we are going to present our results for conjugacy classes in the form of a table again, but this table is slightly different. What this table does is that for every G prime, it lists IGG Prime, where this IG is actually the inner automorphism generated by small g. The nomenclature which I said will explain later on in a later lecture. But IGG prime simply means G prime G inverse. Now you can easily figure out what IGG prime is going to be for a given G prime and G by either using the multiplication table for the group that we had already formulated earlier, or by following up what this G prime G inverse does to an arbitrary point on a triangle. The same technique as the one we used when we built up the multiplication table. Anyway, I'm just going to present to you the full table, which is this. I will just point out that, for example, the top line, IE, which is the inner automorphism generated by E. Namely, given any element in the top row here, the element right below that is what E G prime E inverse would produce. Of course, E G prime E inverse always produces G prime itself, which is why this row is completely identical to this one. On this row, on the other hand, this element is A inverse, which of course is E. This one is A inverse, which is A. This one is A inverse, which if you follow the multiplication table will turn out to be C, and so on. Now, how do we figure out the equivalence classes from here, or the conjugacy classes? Simple. Just go down a column. Here this clearly shows that all the elements which are conjugate to E are E and nothing else, which is why the identity sets in its own singleton set as a conjugacy class. On the other hand, if you look at these two columns, the ones labeled on the top by D and F, you just see D and F recurring, which is why you have a two-element conjugacy class built out of D and F. And these columns clearly show that A, B and C are conjugate to each other and they form their own conjugacy class. So our 6-element group S3, the group of all symmetry elements of an equilateral triangle or the set of all permutations of 3 objects, can be broken up into 3 conjugacy classes. C1, which is the singleton set, the identity. C2, which has 2 elements, D and F. C3, which has 3 elements, A, B and C. By the way, it's not at all true that conjugacy classes will all have different number of elements. As we just saw, for an abelian group, every conjugacy class has the same number of elements. So the fact that we could label the conjugacy classes C1, C2, C3 and they happen to have 1, 2 and 3 elements respectively is more of a coincidence. One thing you can see here, these 3 things which are in the same conjugacy class are all reflections, whereas these 2 in the same conjugacy class are rotations. By the way, this is not to say that all rotations will always be clubbed together in a conjugacy class. You can see that right here because this element, identity, is also a rotation. Remember, a rotation through 0 degrees, and it is sitting on a conjugacy class by its own. These 3 are all reflections. They all sit in the same conjugacy class in this particular group. In a different group, things may be slightly different. Later on, when we talk about the rotation group and the orthogonal group, which includes rotations and reflections both, we will discuss this issue about conjugacy classes there in some detail. For the time being, let me just point out one thing. If your group has rotations and reflections as operations, a conjugacy class will never contain a rotation and a reflection at the same time. So, rotations and reflections always sit in different conjugacy classes. Just to see this in some more detail, Let us take a look at a slightly bigger symmetry group. In fact, the symmetry group of the next regular polygon. If you move one step up from the equilateral triangle, you get a square. And what are the symmetries of a square? Well, you can easily see that one of the symmetries, the most obvious one, is do nothing. That's the E. Then let us go through the rotations one by one. The smallest rotation, smallest non-zero rotation, which will leave the square the same, is through pi by 2 or 90 degrees. That's what we are going to call F. You might wonder why we are calling this F. Well, because A, B, C, D have already been taken or will be taken by 4 reflections, and E of course is the identity. Now we have F, then G, which is rotation by pi, then H, which is rotation by 3 pi by 2, and of course the next rotation will be rotation by 4 pi by 2, which is 2 pi, which is same as identity or doing nothing. So E, F, G, H, 4 rotations. By the way, just to help you recapitulate some of the things we had done earlier, just these 4 would have made a cyclic group of 4 elements. In addition, you have reflections. This reflection along a midline, that's A. This reflection along the other midline, that's another reflection, that's B. Then we have 2 other reflections for the square, which are reflections above the diagonal of the square or diagonals of the square. A, B, C and D. 4 reflections. You can easily build up the multiplication table for this group. It will be an 8 by 8 table. And let me leave that job as an exercise. And using that multiplication table, or simply by following what happens to an arbitrary point on the square, you can easily find out which of these 8 elements are conjugate to the others, and hence write down the conjugacy classes. In this case, you will find that there are 5 conjugacy classes. Identity, as always, is sitting on a conjugacy class of its own. In fact, here there is another element which sits in its own conjugacy class, C2, which is just the 180 degree rotation, nothing else. C3, 2 rotations through 90 and 270 degrees. C4 is composed of 2 reflections, the 2 midline reflections, and C5 are the 2 diagonal reflections. So notice that A, B, C and D are all reflections, but they don't all sit in the same class. Well, E, G, F and H are also all rotations, but they don't sit in the same class. Once again, there's a deep geometric significance to which rotations sit in the same class, which reflections sit in the same class, but we will talk about that later when we talk about ON and its subgroups, the point groups for crystallography. There, these kind of conjugacy classes made out of rotations and reflections will become very, very important. As a final example for conjugacy class structure of a group, we will look at conjugacy classes for Sn. We have already seen what happens with S3, but let us take a look at Sn in general, where Sn, remember, is a set of all permutations of n objects. Now, it is actually rather easy to see that there is a deep connection between conjugacy classes for Sn and number theoretical things like partitions of integers. Let me just motivate that a bit for you today. We will see this in much greater detail when we talk about the representation theory for the symmetry group in a later lecture. Now, in order to see this connection, let us start by taking 2 permutations, pi and sigma, both of which are in Sn. They are both permutations of n objects. And let us ask ourselves, what does sigma pi sigma inverse do? Well, actually, this maps sigma I to sigma pi I. Why? Well, you just feed sigma I to this sigma pi sigma inverse, and using the fact that sigma inverse undoes the sigma, this is just pi acting on I, permutation of the ith object, and then sigma acts on this. So, what sigma pi sigma inverse does, as I have said, is take sigma I to sigma pi I. Now, to illustrate what this means, Let me just show you what will happen for a particular permutation. So, let us take, for example, this permutation pi, which has a cycle 1, 3, 4, 6, 2, which remember means 1 goes to 3, 3 goes to 4, 4 goes to 6, 6 goes to 2, and 2 goes back to 1. And another cycle 5, 8, 7. 5 goes to 8, 8 goes to 7, 7 goes to 5. And let us take another permutation sigma as an example. 1, 4, 3, a cycle, 2, 6, another cycle, and another 3 cycle, 5, 7, 8. So what will sigma pi sigma inverse do? Well, pi takes 1 to 3. What sigma pi sigma inverse will do, it will take sigma 1 to sigma 3, and then sigma 3 to sigma 4, then sigma 4 to sigma 6, sigma 6 to sigma 2, and sigma 2 back to sigma 1. So instead of the cycle 1, 3, 4, 6, 2 back to 1, which pi had, sigma pi sigma inverse will actually have the cycle sigma 1, sigma 3, sigma 4, sigma 6, sigma 2, and then back to sigma 1. Similarly, since pi takes 5 to 8, and that to 7, and that back to 5, sigma pi sigma inverse will take sigma 5 to sigma 8, sigma 8 to sigma 7, and sigma 7 back to sigma 5. And of course, I can immediately read off what this is going to be by looking at this example for sigma and writing down what sigma 1 is, what sigma 3 is, and so on. And we'll end up getting 4, 1, 3, 2, 6 back to 4 as one cycle, and the 5, 8, 7 that was originally the cycle for pi becomes another cycle 7, 5, 8. Now the precise entries in the cycle structure are really not of great concern for us right now. But what is very important is this. Sigma pi sigma inverse, of course, is an element of Sn which is conjugate to pi. And notice, pi had a 5 cycle and a 3 cycle. Sigma pi sigma inverse also has a 5 cycle and a 3 cycle. It will take just a moment's thought to understand that this has to be the case. Since sigma pi sigma inverse maps sigma I to sigma pi I, the cycle structure of pi and the cycle structure of sigma pi sigma inverse have to be the same. In fact, the converse is also true, and that also is not very difficult to figure out. If you give me any two permutations with the same cycle structure, that is the same number of 1 cycles, 2 cycles, 3 cycles, and so on, I can find out a sigma which will make the two permutations conjugate to each other. That is to say, in general, any two permutations with the same cycle structure belong to the same conjugacy class, and vice versa. That means the cycle structure completely determines which class an element belongs to. Now, the cycle structure essentially says in how many different ways can you break up the integer n into pieces. And this breaking up of an integer into non-negative pieces is what is called a partition of the integer in number theory. And what we are really seeing here is that there is a deep connection between conjugacy classes of Sn and partitions of the integer n. Now this connection will be very, very important in determining the theory behind the representations of the symmetry group. We will come back to this theme of conjugacy classes over and over again during the course of these lectures. But for the time being, let me just stop this particular lecture here. We will go on to a different topic in the next lecture, and that will essentially have to deal with a question that might have already arisen in some of your minds. When we figured out the cosets for the symmetry group of the equilateral triangle, we found that for some subgroups, the right cosets and the left cosets were distinct, whereas for another subgroup, the right cosets and left cosets were identical. You might have asked yourselves, is there something special about that particular kind of subgroup for which the right and left cosets coincide? The answer is yes. Such subgroups for which right and left cosets coincide are very special. They are called normal subgroups, and they will be the theme of our next lecture.